Okay, so this is our MEE 390 lab number 3, Aerodynamic Drag Analysis Lab. We're group number 8. I'm Spencer Sapolskis.
I'm Wes Black.
I'm Limar Bernardo.
I'm Edgar Gamboa.
I'm Juan Escobedo.
And this is our presentation on the wind tunnel aerodynamic drag analysis lab.
The purpose of this experiment was to view how drag force can vary depending on the shape of an object placed inside of a wind tunnel using the drag force equation shown below. The force and velocity were collected with a dual range force sensor and anemometer respectively. The data for each shape will be compared and regression will be generated.
For the methodology section, we started with our experimental setup, which consisted of a dual range force sensor. The 3 shapes we chose were hemisphere, pyramid, and then the cube. Anemometer, anemometer to record the wind speeds at different hertz levels, and as well as the Vernier DAC and then the Vernier app on the smartphone to record. So for the process, we set the turned on the wind tunnel, set it to the hertz we want our first hertz level. We attached the shape to the force sensor, recorded the offset of that force, the offset of that shape on the force, waited for the wind tunnel to reach a steady state, and using the anemometer, we recorded the velocity for that hertz level. After that, we recorded the drag force for each shape at 3 different hertz levels, and as well as measured the calculated affected area of each shape.
Here we could see the plot of the regression for the wind tunnel driving frequency versus the wind tunnel velocity at 95% confidence interval. The fit appears to be very good, and the error bars on our data are very small, which indicates that our data collection was precise.
After we did the regression on the wind tunnel velocity to get down, exactly what velocity we were using, then we were able to plot the true mean velocity versus the magnitude of drag force for each object. And as you can see, the square pyramid and the hemisphere follow a very rough, kind of increasing trend, which would be characteristic of what drag force should do. But the cube had some higher uncertainty in it and is kind of, not following the exact cubic trend or square trend of what drag force would be. But that's probably due to the high uncertainty in our data. Then we were able to calculate drag coefficients based off of the drag formula, rearranging it. If you multiply 2 times the drag force divided by the frontal area times the density times the velocity squared, you can get the drag coefficient. And this table here organizes the various wind velocities in meters per second based off of the drag coefficients that we calculated. And as you can see, as the velocity increases, the drag coefficient gets closer and closer to the reference drag coefficient. And I believe this is due to the Reynolds number of the flow, where Reynolds number is defined as density times velocity times the length of the object divided by the fluid's viscosity. So as the Reynolds number gets higher, it's going to get closer towards the reference drag coefficient values because the reference drag coefficient values were taken at a Reynolds number of 40,000 or higher. And so basically, our drag coefficients are, agreeing with the literature, which is good.
For our outlier analysis, we did a similar method to lab 1. We used 95% confidence interval using a MATLAB code. After running the data with our code, we found that none of the points or values failed the 95% interval. However, we did have two values that are suspect and are much higher than all the other values for that force and Hertz level. This could be due to transcription errors, so we think it's best to remove these 2 points out of this data.
This is our error analysis. We had some potential sources of error, which could have affected the accuracy of our results. The first one was the major source of error was from how the instruments were handled. The anemometer and the dual range force sensor were held by the hand rather than being fixed. This introduces like small movements and vibrations, which can lead to fluctuations in the velocity and the force readings. Secondly, the position and limitations of the sensors also contribute to the uncertainty. Each measurement device has a certain resolution and margin of error, which can slightly affect the recorded values. Another possible sources of error is human error, which include incorrect readings or recording values. Finally, fluctuations in wind speed over time within the wind tunnel can impact the results. Even with steady state conditions, small variations in airflow can cause inconsistencies in the measured drag force.
So overall, our results showed that drag force increases a lot as velocity increases, which makes sense because velocity is squared in the drag equation. We also saw that the shape of the object really matters. The cube had the highest drag since it's a blunt shape, and it disrupts the airflow more, while the hemisphere had the lowest drag because it's more streamlined and it lets the airflow around it more smoothly. Our results mostly follow what we expected, but there were some sources of error. For example, the force sensor might not have been perfectly calibrated, and even small things like how we held the anemometer could have affected the airflow. Also, a couple of the hemisphere data points at the high speed looked a little bit off compared to the rest, so this might not be a completely reliable. If we were to improve this experiment, we probably focus on getting more accurate measurements by improving calibration and maybe automating the velocity readings so there's less human error. And running more trials would also help make the data more consistent.
And that seems to be it. Good work,
Right,
team.